Hello and welcome to this tutorial on balancing chemical equations. There are 3 chemical equations that we will look at and we will balance each of them. If you are a beginner, I would recommend that you draw the tables much like the ones drawn on the left and the right of the screen. It just helps, in a way, visualize and keep it a little more neat. The first thing you need to ask yourself is, are there the same number of particular atoms on either side of the equation? If we look at the one given, is there the same number of oxygen on the left-hand side as there is on the right-hand side? On the left-hand side, this is when you use your table, we have 2 oxygens. On the right-hand side, we only have 1 oxygen. It is at this stage that you can see that is clearly not balanced. What about the hydrogens? How many hydrogens do we have on the left? We have 2. What about on the right? We also have 2. Despite that, we still have an unbalanced oxygen ratio. This is when we bring in the big guns. Let's bring in these coefficients. The coefficients are the big numbers that go at the front of your molecule or at the front of your compound. So if on the left-hand side we have 2 oxygens, but on the right we only have 1, we are able to do the big number 2 coefficient at the front of the water molecule. What this looks like is saying we have 2 lots of water molecules which look like this. This is a water molecule. That's 1 lot. That's what it looked like before. But we have 2 lots thanks to the green coefficient. And there you go. Now that we have 2 lots, how many oxygens do we have on the right-hand side? We have 1 right here and 1 right there. So now our new number is 2. However, how many hydrogens do we have? On the left-hand side we have 2 hydrogens, but because we changed it or we placed the coefficient on the right-hand side, we have 2 lots of water molecules. We have 1 hydrogen there, 2, 3, 4. Our new number is 4. But hold on the left-hand side, we only have 2. So, we need to bring out the other big guns and we need to place another coefficient. And to balance that out, you could place a 2 right at the front there. Which then means we have, let's draw this out. This is a hydrogen gas molecule. It's a diatomic molecule. That's one of them, but we have 2 of them. And all up, how many hydrogens do we have on the left-hand side? We have 1, 2, 3, 4. This is good. On the left-hand side, we have 2 oxygen atoms. On the right, we have 2. On the left, we have 4 hydrogen and 4 on the right. Perfect. Let's try something a little more complex. The first thing you need to ask yourself is, how many irons do we have on the left-hand side? Fe is iron. We have 1. How many Fe's do we have on the right-hand side? We have 2, thanks to the little subscript. It is not balanced. Let's have a look at oxygen. How many do we have on the reactant side? We have 2. How many on the right-hand side? We have 3. This one is a little more complex. I find that the best way to balance chemical equations is the process of elimination. So let's grab our big coefficients. If we have 2 iron on the right-hand side, let's put the number 2 on the left-hand side. So now we have 2 lots of iron. This is good. 2 on the left, 2 on the right. Perfect. Yet our oxygens are not balanced. To balance them out and to get the number 3 on the left-hand side, you will, in hindsight, you could do something that looks like that. So 1.5 times 2, which will give you 3, and then that would be balanced. But that is just confusing. As soon as you have a 1.5 and not a whole number, nobody likes you. Get rid of those and let's use whole numbers. If we were going to use a 1.5, if we times that then by 2, we would get 3, which is a whole number. So if we change this to 3, we now have 6 oxygens. I hope you can see that. We have it's a diatomic, it is a diatomic molecule. That's 1O2. That's another one. This is another one. And all up, we have 1, 2, 3, 4, 5, 6 oxygens. Perfect. But on the right-hand side, we only have 3. So that is an easy fix. If we only have 3, if we place a coefficient of 2 at the front, we now have 2 lots of 3. We have 2 times 3 will give us 6. Therefore, we have 6 oxygens on the right-hand side. Yet, how many ions do we have on the right-hand side? Now, like I said, it's a process of elimination, and all of a sudden it throws it out of balance. If I draw it, maybe it'll be easier. The iron oxide molecule looks like this. For simplicity's sake, Fe, that's 1. And then let's do another one. Because now we have said we have 2 of them. All up, how many oxygens do we have? We have established that we have 1, 2, 3, 4, 5, 6. Yet how many ions do we have? Well, we have 1, 2, 3, 4. So we have to scribble this out, and now our new number is 4. Where on the left-hand side, we only have 2. But this, thank goodness, is an easy fix. If we change this coefficient, we change it all, and we change it to a 4. That is simple and easy. Now we have 4 ions on the left-hand side. Now this one has 3 different types of atoms, so this one is where it can get a bit tricky. This is why having these tables that are drawn are very helpful. Alright, so let's begin with carbon. How many carbons do we have? We have 1 carbon on the left-hand side. So we have 1 carbon on the left-hand side. How many do we have on the right? We have 1. So far, so good. How many hydrogens do we have on the left-hand side? We have 4. How many do we have on the 4? How many do we have on the right? We have 1. This is not good. This is not balanced. This is when we need to come in. Now let's choose blue. How many chlorines do we have? We have 2 on that side. How many on the right-hand side? We have 4 and another one right there, 5. This is not balanced. This is when we do the process of elimination using coefficients and try to balance it out. Let's begin to balance using the coefficients. I would start off, as carbon is already balanced, let's start off with the hydrogens. On the left we have 4, on the right we only have 1. So if we put a large 4, a coefficient at the front of hydrochloric acid, the HCl, we now have 4 lots of HCl, which looks like this. We have 1, 2, 3, 4. Which makes us have 1 hydrogen, 2 hydrogen, 3, 4. We now have 4 hydrogens. So far it looks balanced for the hydrogens, but notice how when we increased the number of hydrochloric acids, we also increased the number of chlorines. So how many chlorines do we have? We have 1, 2, 3, oh, I don't know what that was, 4. We now have 4, and we also have these 4 from before. So we now have 8. On the right-hand side, we have 8 chlorines. On the left-hand side, we only have 2. But that is an easy fix. Let's use our coefficients. If we only have 2 on the left-hand side, if we do a large 4 right there, because 4 times 2 equals 8, we then have a balanced chlorine. And to show you what that looks like, it's a diatomic molecule, which means it's chlorine with chlorine. There we go, chlorine. And how many of these do we have? We have 4 of them. So how many all up of these chlorines do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. And that's what we have there. We have 1 carbon, 4 hydrogens, and 8. And to neaten it up a little bit, the coefficient is 4 there and 4 there. I hope this has made things a little more clearer. If you have any more questions, don't be afraid to ask me in class. I look forward to seeing you then. Thank you.